Welcome and thank you for attending the second webinar in our series introducing our course on animal-free safety assessment. Today's topic will be predictive chemistry, in silico tools, and read across. My name's Catherine Willett. I'm from Humane Society International. I'll be introducing the AFSA Collaboration as well as the education and training program. Then following the introduction will be our main presentation by Detroyer from L'Oreal and Wendy Simpson from Unilever, which will be followed by a brief Slido quiz, which is based on the learning objectives in the main talk. So please pay attention to those. And then followed by a few minutes for Q&A. If any questions come up during the webinar, please enter them into the Zoom Q&A. We'll either answer the questions in a written form during the webinar, or we'll try to get to them after, at the end of the session. Okay, so now for the introduction. Okay, the Animal-Free Safety Assessment Collaboration is a group of industry and nonprofit partners who have the joint ambition of accelerating global adoption of modern species-relevant approaches for safety assessment, with a particular focus on cosmetics, chemicals, and biologicals. The project is coordinated by Humane Society International. The AFSA Cosmetics Education and Training Program that we're introducing through this series of webinars is a part of the cosmetics workstream. So about the course, the scope of the course is safety assessment of cosmetics and cosmetic ingredients without new animal data. It covers all aspects of the safety assessment process and includes things like consumer exposure, both external exposure and internal exposure. It covers how to assess different types of effects, including the acute local effects and everything through systemic repeat effects. And it also covers how to integrate this information to make a safety decision. What is unique about this course is that it really focuses on understanding the information generated from these tools and how to use this information to make decisions. And what it is not is a tutorial about how to perform or develop the individual methods. This course is really intended to complement existing courses and webinars that cover how to perform the methods. So the purpose of this program is really to address the needs of the regulatory and regulated communities, as well as the other stakeholders that are involved in the risk assessment process of products. And the ultimate goal is to support regional capacity building throughout the globe to achieve long-term acceptance and implementation of non-animal approaches to safety assessment. So as a context for this course, I just want to talk a little bit about the safety, what an animal-free safety assessment process is, or at least what we mean by it. Okay, so here as a very, very high level comparison of a historical risk assessment process on the left versus what we're calling animal-free risk assessment on the right. And the basic processes between the two are quite similar. Both rely on measurements or estimates of exposure, as well as estimates of a chemical's intrinsic hazard or bioactivity to determine the risk associated with a particular use or exposure. The main differences are in how and when exposure comes into the process, and as well as the types of information that are used to estimate a chemical's intrinsic hazard or bioactivity. In a traditional risk assessment, a set of standard animal tests, generally speaking, is performed, and the lowest dose causing an effect or the highest dose causing no effect in any of the tests is taken as a point of departure to base the risk assessment on. Exposure generally considered only after or at the same time as the hazard assessment, and then both feed into the final risk assessment. In the animal-free risk assessment, especially for consumer products, exposure is considered at the beginning, and assessment is performed in a series of stages. Exposure considerations are used either to make an early safety determination or to design strategies that generate the information needed to make a safety determination. In silico tools that we're going to hear about today are used in the initial characterization and in read across, and let's see, any needed information on biological activity or internal exposures generated using non-animal assessment methods. Finally, the results of the biological activity is compared with the measured or predicted internal concentrations to generate a margin of exposure, which is then used to conclude the risk for a given use or exposure scenario. And of course, that's a gross generalization of the process. But anyway, how are the education and training program, in our program, we have taken this complete process, which is diagrammed in the gray boxes above, and divided it into 8 modules for content development as diagrammed in the purple boxes. Each of the modules are structured around learning objectives, and we've also included another module on the global regulatory environment for chemicals and chemical ingredients or industrial chemicals. So the basic animal-free risk assessment framework for personal products has been quite developed by a number of industry and regulatory partners, and it's also called next generation risk assessment. And this shows the NGRA framework that was originally developed as part of a European framework program called SAR-Decision, which is animal evaluation, safety evaluation, ultimately replacing animal testing. And in this framework, there are this framework can be loosely divided into 3 tiers, and the third. So the first tier sets up the problem formulation. So it's the context of the decision. And in the problem formulation, you collect all existing information and evaluate it to see if you can make a decision. You also do initial in silico predictions, and here you can create an initial mode of action hypothesis. At the same time, you do the initial exposure estimation or consumer exposure estimation, and you can use this also to exit here if you can use the threshold of toxicological concern, or you can identify a suitable analog for read across. If the assessment requires the generation of new information, you progress on to tier 1, where you use in vitro methods to begin your hazard or bioactivity characterization and begin to collect those concentration response curves for the activity. And at the same time, you start to explore internal dosimetry and look at things like metabolism and such. And here you can exit either based on an internal toxicological threshold of concern, or in a comparison, determination of the margin of exposure, which is a comparison of the in vitro bioactivity with the internal exposure. If you still need more certainty, or you cannot yet make a risk conclusion with sufficient certainty, then you go to a tier 2, where you refine your bioactivity information, and you also can look in more detail at the internal exposure. And again, then refine your margin of exposure characterization here. And the goal is to ultimately come to a risk assessment conclusion of either high or low risk for that particular exposure scenario. So that's just a more detailed way of explaining what I just explained. And then I will, so now I'll show you how the modules cover this entire process from beginning to end. So the problem formulation module covers problem formulation and all of the things that go into that. And the consumer exposure, there's a module in consumer exposure that covers things like use scenario, consumer habits and practices, and the different modeling techniques that you use to get different levels of certainty around your consumer exposure estimate. And then what we're going to be hearing about today is the module on predictive chemistry, which includes in silico tools and the data that goes into them and how you use them. And it also includes a section on read across, identifying analogs and read across. We have a separate module on exposure-based labeling, which covers the concept of toxicological threshold of concern for 3 different routes of exposure. And there is a separate module on the history of safe use for complex extracts and biologicals. There's a module on internal exposure dosimetry, which covers all the absorption, distribution, metabolism, and excretion, as well as how you estimate concentrations in target organs and systemic bioavailability through PBK modeling. It also covers in vitro to in vivo extrapolation. The in vitro data synthesis module covers in vitro data, the types of tools used to generate the data, and how the different data can be combined to inform hazard or bioactivity identification and characterization. And then finally, there's the module on integrating it all into a risk assessment. And this talks a lot about how you would determine a margin of exposure. And this is also, this module contains a lot of case examples for different problem formulations. So different decision, everything from endpoint specific decisions such as skin and eye irritation and skin sensitization to more comprehensive risk assessment for repeat dose systemic exposures. So from this, you can kind of get the picture that this course is quite comprehensive. It's also fairly in-depth. The modules, just to let you know, the modules are at different stages of development at the moment. And the ones that are farthest along are the subject of this current webinar series, and these will be ready for dissemination shortly. The rest of the modules are coming later this year and will be the subject of future webinars. So here are our partners in this project, and these are the partners that are contributing, the experts who are creating the content for the modules. And here's a list of the authors, the experts that are authoring the content of the modules. And in addition, we have education experts and stuff helping us make this into an education and training program. Okay, so today we're hearing about the module on predictive chemistry in silico tools and read across by 2 of the authors, Anne Detroyer from L'Oreal and Wendy Simpson from Unilever. Anne is a senior research scientist with expertise in the field of in silico modeling at L'Oreal Research and Innovation, and she holds a PhD in pharmaceutical sciences. Wendy's a computational chemist who has worked in the Safety and Environment Assurance Center at Unilever for nearly 15 years. Her main roles are to support the safety assessment of new ingredients, including in silico approaches, and to support the REACH registration of substances using non-animal approaches and next generation risk assessment. So I will turn it over to Anne, who will then turn it over to Wendy for our main presentation.
Oh. Hello, everybody. Thank you, Kate. So in the next step, giving the short outline, I'll be starting indeed talking about the in silico tools. And as Kate indicated, then Wendy will take over and give you some more information of what read across is all about. So let's get started on the first of our sessions on in silico tools. Kate, if you can change the slide. Now, of course, within these two, sessions, there's some learning objectives that you see here described on the screen that we hope that with regard to the presentation we're giving you will help you actually tick off all these issues, and they'll be discussed in several steps. Okay, can you switch? Now, when it comes to in silico prediction tools, and that is, I think, with Wendy, something that we wanted to give put some emphasis on, is that in silico tools globally, which contains the in silico prediction models, of which we're going to talk, and also the read across, of which Wendy is going to talk. They are, as you saw on the NGRA explanation that Kate gave, they are really in the first step of this risk assessment evaluation, the first tools that we can start using when we're working with this framework. As such, because the reason why this is because this is all in silico happening on a computer. And we only use the computer and the information that's in the computer being coming from databases or being generated by in silico prediction models, which I will explain you later. And as such, that means that these tools are and can be very accessible, and the creation of new data, the generation of new data or hypothesis can be quite not costly and very quick in time. And that's also why they are put in the first step, and they are very much used at every steps of a risk assessment generation, but especially in the first steps. As such, as we'll explain, it should be clear from what we're presenting, is that in silico predictions and predictions, they should be able to support your risk assessment, as it was indicated in the NGRA framework by Kate, they're just not giving predictions. They're also can help you on forming hypothesis generation as to go towards the next tier steps, and give you an orientation of which other alternative tests you best orient towards, seeing the indications that in silico predictions information can give you. Of course, prediction can predict biological property, and is very much used, this information, in your dossiers as weight of evidence. This has been described by Eka in his descriptions, and several other regulatory instances that we can use them already for our submissions in dossiers. Of course, what you will also see is that in silico methods, with regards maybe to in vitro methods and other alternative methods, they have to be very well documented, and they have to be very, very transparent, which is a very important requirement that's always coming forward when we're discussing with regulatory instances on these as in silico methods as part of the alternative methods. So with this start, let's change slide, Kate, and really start on what actually in silico prediction models are all about. I talked about in silico tools, which globally concern all techniques that are just happening on a computer. So in silico prediction models, and also later on some of the read across that Wendy will explain. Now, when it comes to really prediction, in silico predictions, what you have to keep in mind is that there are actually three essential elements that go into the prediction models that you have to take into account. On the one hand, there is the endpoint, the information, the biological information, the activity that you want to have a prediction or information about. Right? This you have to be very clear about, and this, when you start building a model or using it, you have to know what your endpoint, your goal is. And if you start building a model, you have to very well know the biological information that you want to simulate. Second element when building a model is, especially silico prediction models, is you have to be very sure about the chemicals that are supposed to have caused the biological effects. in the test and what they are exactly, and their description is, and what their chemical descriptions is, and it has to be as clear as proper as possible. So we have the biological endpoint information you want to model, then you have the information on the raw materials that are supposed to cause or have caused certain effects, and you need to be very clear or have this kind of description, obtain it. Once you have these two elements, what will happen in prediction models, the idea is that we're going to try to relate, and we're going to try to find a relationship between the chemical causing the activity and the activity itself. And this relationship uncovering can happen through different kinds of techniques, and that is where actually all the different kind of terms that come out, and that we'll see in the next slide of the presentation will come out. But these three elements, so the biological activity, the chemical information, and the uncovering techniques, the different techniques, once you start applying them, then you'll start constructing a prediction model, which is globally termed SAR-QSAR models, which you might have heard already before. Now, if you go into to have a good understanding when you start using, or you want to start applying in silico models, it's also very important that you know a bit about how they are constructed and which elements in the construction are quite important to take into account as to assure you when you're applying them that you will have a good understanding of what's happening. And that's why we presented here to you here the typical process of an in silico modeling, which contains the first development, quite a few development steps before going into application. You have to know is that this is not just a linear process. What happens in reality is that we might develop, apply, and when applying, we might also go back to the development stage to kind of make the model better and better. So in reality, this can kind of be a loop when it comes to developing an in silico model. So when we now focus on the first step of our process, as you understand, we need to have the biological data to build activity data to build our model on the one hand, and finding these data can be done. There's public resources, but in case of companies, we can also have proprietary data that we have and we collect on the one hand. In the next step, what will happen when we have this data collected and found in the resources is a very important step for people building the models, but also very important if you're applying it to understand. The next step is about curating data. I think, Kate, we have some information on the data curation. Data curation is once you've got your information, what you want to make sure is that the data that you're putting into your model, be it really the measured results of which you're going to construct your models, as the information on the chemicals that have been causing the measured effects, that it is as clean and as understood as possible. Because a very basic rule is that if there's rubbish data going into a model, there will be rubbish out. The model will never be good. So that's a very important step that we'll always take into account. And when it comes, for example, to the measured data, this means that we'll have a look if this source of the data is quite reliable, if there's a good description of the protocol, what's the repeatability of these data, are there duplicates on the one hand, so that's purely on the biological information, and on the other hand, we'll have a look at is the description of the chemicals that are supposed to be linked to this information, is this clear enough? Are we sure that when we're talking about mixtures, this is, for example, mixtures and there's no pure chemical structure that can be derived? Are we real about the chemical information that is supposed to be linked to the biological information? And there's a lot of cleaning and verifications going into that step. Also, more importantly, especially on chemicals, and that's what I expressed in the next slide, Kate, is that what we always have to take into account is that we make sure that we know which chemical is supposed to have caused the in our case for safety assessment, toxicological effect. Because sometimes what happens is that a parent chemical will actually undergo some transformation before it's actually giving the biological effect. And I put the example of limonene, for example. For limonens is the skin sensitization. Actually, it's not the one that's responsible for a skin sensitization effect. It's actually its product of autooxidation that is responsible for the skin sensitization effect. So it's important to realize that and to kind of build that when you start building a model, to build that into the model, that information if you have it, because that will make the relationship much better. In the next step, when everything is built, what's also happening is that for users, sometimes even these kind of chemical simulator models, so models that will automatically build in the transformation from your limonene to your autooxidation products that are shown, can also be introduced into a QSAR models, so you yourself don't have to think about all of that. But it's always good when building this model that you realize that, and also when you're applying the model. Welcome on to that. So once we have, go to the next slide, once we have cleaned all this information, then indeed we can start trying to find a relationship between these both elements, and the techniques that are used globally when it comes to in silico prediction or safety assessment. They're kind of can be separated in two kind of great big techniques, which is on the one hand we call SAR techniques, structure activity techniques, and on the other hand some QSAR techniques. The main big difference between the two is that when it comes to SAR techniques, it's all about much more about decision tree, about expert knowledge that is expressed and that is used to kind of find the relationship. But when it comes to QSAR, that's where actually we'll see that there's more application of statistical models and techniques to be able to go deeper into the relationship. And of course, everything is possible. A combination of both, using expertise and statistics together, can also be used. And that's when they called kind of globally hybrid in silico models. Now, let's just have a closer look at what SAR models are, for those comprehensive. So when it comes to structure activity models, as I said, globally what's going to happen is we're going to look for a relationship between the absence and the presence of an activity of a specific chemical, and we're going to look for certain features, patterns, or globally mechanisms of the chemical based on its chemical structure that might be responsible for that for giving an activity. So in that sense, and this relationship, looking for this information, will mostly be done by experts looking at the information and introducing a mechanistic knowledge or a transformation that they know happens. And as such, SAR models then will actually describe certain patterns or certain mechanistic transformations that might happen to a chemical, and that explains its activity in our case. And because it's so focused on explaining an activity and not an absence of activity, very often these models are also called alert models, because they're mainly focusing on finding or alerting on an effect and not on an absence of effect. And now what happens also is that these kinds of models, because they describe mechanisms, or they indicate very big structural patterns that might be important for the effect, they can be used also to group your chemicals within categories that show the same mechanism of action. And in that case, they might be also called, also be grouped under the name of profilers when they're used in that sense, used like profilers, and in that sense also indicate, not only give a prediction, but indicate a mechanism and maybe point towards what your next in vitro testing or hypothesis building should be for your in vitro testing to follow on. An example of, there are many of these SAR models that are out there on the different relevant endpoints for safety assessments of cosmetics. But one of the platforms, in silico platforms, in which has quite a few SAR models, is a toxtree platform, co-created or instigated by the GRC. And here you see an example of one of these SAR models, which is skin sensitization, where basically people have been coding mechanisms that were related to chemical transformation mechanisms that are related actually to an option of chemical binding to a skin protein and potentially giving sensitization. And basically there are 6 mechanisms that have been described, main mechanisms by experts. These have been encoded, and what happens in the system is once you put your chemical structure in this case the paraphenylene diamine, well, the patterns of this paraphenylene diamine will be compared to will be going from testing one mechanism after the other, and if its chemical pattern confers with this mechanism, it will flag and an alert will be given. And in this case, for example, the mechanism of Michael acceptors creation for a paraphenylene diamine has been flagged, and thus you get alerted that you can potentially have a skin sensitization reaction with this molecule. That's basically what it's all about. Now, if we go to a next step, you can see, yes. So this was also about SAR models, about mechanistic information, about experts, knowing that you have the decision tree, you have more pushed experts models that are and platforms that are available out there, like direct systems, for example. When it comes to actually, when you have information that is much more of a quantitative nature, be it your activity that you want to have more of a, instead of a yes/no information, more of a classification information, or even a more continuous information, like an LD50 prediction, you might go more to towards the construction or the use of a QSAR model. And what happens is that when you have your biological information that is of much more quantitative nature, just mechanism information might not suffice to uncover the affinities of this relationship. And what will happen is you'll go towards the construction of QSAR models, and you'll use your description of your chemical description that you're putting on the other side. You'll try to refine it to a much bigger extent, and this refinement, the description to much finer extent, is what often is expressed with what we call descriptors, and which computational chemists, they do have a lot of these chemical descriptors in face, and that's what we'll be using in QSAR models. Another difference between SAR models is that on this whole of information, then instead of just these mechanism rules or expert eye, we'll use statistics to kind of pull out the right relationships. So if we go to the next slide, I'll just pointing out a bit of the importance of the two main differences when it comes to QSAR. What are molecular descriptors? As that molecular descriptors, well, what you basically use is what you use in any in silico model. You have your chemical structure and you're going to have a look at it. And as I said, with computational chemists, they have descriptors linked to all different kind of dimensions that a chemical structure can take. It can go from 0 dimensions, and a chemical descriptor that's very known to all of our users is molecular weight, for example. This is 0D descriptor is very used in a lot of models and very explicative. This is a very 0D descriptor that can be calculated starting from the structure, and we can go up in dimensions as we want to go up and refine to get to certain informations. For example, the substructures of which I'm talking to typically can be 2-dimensional descriptors that can be used into your models and can be indicated. We can go to even higher levels of dimensions of optimizing our chemical structures. And that's when, in case, for example, your endpoint, when it's linked to, when you need to, for example, your endpoint is linked to a receptor binding, the activity is linked to a receptor binding that will happen at one point. This is very much a 3D structure interaction between your chemical and receptor is very important in that sense. So then at that case, we'll go and look for molecular descriptors that will describe this 3D structure and thus will be relevant for potentially describing this interaction, this biological activity, and thus will explain the relationship and will make actually a prediction possible. And we can even go to 4D when there's actually it's about looking into electronic effects. So as you can see, a lot of potential molecular descriptors just based on chemical structure that can be created. And it is important when you have an idea of your biological activity and you want to model it, to have an idea of what is potentially important for the interaction to happen. And that's how sometimes part of the choice is made on which descriptors we're going to use or not in the model. Other part that we can use is then, of course, the statistical technique that will apply to uncover the relationship between the descriptors that are proposed between your activity. And as I said, there's a lot of different statistical techniques that are and names that are out there. The way that a developer would choose the model, it's important to know that there are some factors that will drive the choice for one technique above another. That can be the amount of data that we have. If there's really a lot of data, we might need to have some deep diving into information. If the relationship, the prediction that we want to make, do we want to make do we want to predict classes, or do we want to predict a continuous value? You won't use the same kind of statistical techniques to find the relationship between your information. This can drive your choice. Do you have some mechanistic or preference information that you can like to push? For example, in Bayesian models, that you can somebody can just push an expertise instead of having just the statistics work for itself. But if you have very complex information that you want to uncover, you might want to have some more deep dive models like neural networks that you want to apply. Anyway, what we have to know is, so this is the key drivers for people choosing these different techniques. Of course, for one and same solution, there might be several techniques that are, even when we're going through all these factors, are useful. So what happens usually is that we would try applying different techniques and then see how the model performs. What are, in the end, it's sensitivity, it's specificity. These terms might speak to you. It's positive predictive values. These kind of factors that we use to evaluate them in different techniques and to, in the end, choose one or the other. So once we have done all that, we have built up QSAR. Can build a SAR model. We know now how to build a QSAR model. But what happens sometimes is that we will use, or both will be used at the same time, will be used actually one after the other. And this is what's called then the hybrid models. And an example of hybrid models can be formed in the Times platform, which is contrary to toxicology platform, privately owned platform, where actually for their skin sensitization model, we see clearly that when you will put in this model your parent molecule, you will in first instance have a metabolic transformation simulator, creating all the potential other chemical structures that are formed even before the activity takes place, which is what we talked about before. And all these different forms of the chemicals then will be evaluated towards the first layer of actually classification, a SAR model, which will check to which potential mechanisms these chemicals might belong and mechanisms that can be important for skin sensitization. And seeing this can give them an idea of sensitizer, non-sensitizer, or alerting information. What has been done also in this model is because one wanted to go further than just have the information sensitizers, non-sensitizer, a QSAR model has then been built in to be able to classify within these groups which one are actually stronger sensitizers than others. So this is typically an example of a hybrid model and the different stages that can be used. Now, when we go to the next slide, Kate. When in practice, we use, so we have all these different models for endpoints, and as a user, you have them in front of them. What often happens is, and it's a very natural tendency, is to think, okay, I have several models that are predicting the same endpoint in silico models. I'll just use them all and I'll try to make a consensus out of that. And it's actually an approach that's studied also in literature. The idea of taking several prediction models and combine them before giving your final conclusion on your prediction. And then what we see is some take a predominant prediction, some make an average prediction. We can even combine them into another model to refine the predictions. All these kind of things can happen. And what I would say is it has the advantage when you start combination that if all the models point in the same direction of information, it might give you as a user the feeling of having a higher confidence on the information and to push forward in your safety assessment. A con can be actually that by using all these different models next to together with one another, that this increases the complexity of actually understanding what happens, what you're doing, and it might actually be holding some people back from using them or using the predictions. So if you're kind of new in the field, I would say take care not to stack or to use too much of the models all at once, and start by using some and getting confidence in using them before trying to combine too much of the models. So that's, I think, a first advice on the application of the models. So when we're going back to our process, yeah, thank you, Kate. Now we've gone through all the steps and some of the important elements that you need to keep in mind when models is developed. And going now to the real applications, as we started doing the consensus models, there are actually, I would say, three key questions that you need to ask yourself when you're applying in silico model within a safety assessment framework to make sure that you get a good assurance on your prediction. And so we'll start diving into these three questions. A first one is ensure that you have the correct chemical structure for input into the model. And this relates to what I was saying before in the presentation. It is actually important to know which chemical you want to test, and to also kind of reflect on the fact that for the endpoint they're going to use, that sometimes this chemical might have been transformed even before it has its activity, and to reflect on that, to maybe even have information on that. Knowing that some models might have built in some simulators to kind of take a part of this reflection over, but it's important that you ask yourself these questions before you start, and you also know if the model automatically creates these potential other chemicals, other forms of the chemical, or if you have to introduce them yourself. So once you have answered this first question and you're quite sure and you're positive, then you can go to the next and ask yourself the next question, which is okay, then we'll have to choose the model that is applicable for your endpoint of interest. Now, how do you choose? In a first step, between all the choices that you have sometimes on different models, the silico model that I proposed, a good model. Well, if we go to the next slide, I'll try to give you some pointers that, that might help you doing that. First of all is knowing the endpoint, the information that you would like to predict, your model to predict. And with the models that are proposed, choose your endpoint, and which in this endpoint, in this model, is actually the information, the clarity information, very well described also. And this is regards to also what I indicated before. The clearer the information is, the purer the information is on the biological activity information that was used to model it, the more clear and probably the better your model will be on that endpoint. That's the first step. Another consideration when choosing a model is a very more pragmatical nature. It's sometimes there are platforms out there containing models that are actually freely available on the internet. That might be a consideration, different from the users. Others are require a license, which makes it a bit less easy of access. But in case of sometimes of industry, it might have the advantage that these pass more of our IT protection safety criteria, might have an advantage that some of the licensed platforms, they do have experts behind them that you can give a short call that can help you give more information than on some freeware. Not always the case, but this is a consideration that sometimes makes also a difference between different users on which model they're going to use. Very pragmatical factors also sometimes also are taken into consideration actually. And a third factor that drives the choice of the model is its state of regulatory acceptance, especially in the case of an NGRA. If we're building up our weight of evidences or for in silico information, sorry, for weight of evidence for in the dossier, it is important that a model has been actually accepted to the highest level of the regulatory instances that you want to submit your dossier to. If you're in the very early stages of safety assessment, you can use other models that haven't pushed yet all the different degrees of acceptance towards these regulatory instances. But that is also a very important stage, and the regulatory acceptance actually and the stage and how to kind of models get to that stage is actually part of our next question and our last question, the important question that you need to ask yourself when using the model. And that is the once you have a prediction, you have your chosen model, you have your prediction, is the assess its reliability. What is my prediction that I'm taking for my chemical out? What is it actually worth, and to what extent can I use it? And assessing this reliability is actually can actually be linked to several criteria that you're going to investigate, and I'm summed up the criteria in the next slide. And as you see, it's fivefold. And this fivefold information is about actually looking into a first information when you've got a prediction is to look into the fact if your chemical that's predicted is in the applicability domain of the model. Usually this is built into a model and it will automatically give you an indication of your molecule is in the applicability domain or it isn't. But basically it's about your new chemical. Does this chemical structure, did I see it before? Is that a chemical structure that's close to all the other chemicals that we have put into the model? If it's not the case, your chemical will be pushed usually out of the applicability domain and it will not be accepted for prediction. So that's the first level of information and reliability. A second is a factor of estimating reliability is the uncertainty. The uncertainty that comes actually expresses the limitation of knowledge or the lack of data that's introduced. And that was what I was talking about when biological data, how it's important to curate your data. It's to get out of all of this uncertainty out. uncertainty linked to process and uncertainty linked to repetitions of your biological data. And it actually should be eliminated as much as possible actually at the stage of building the model. But you can always have a look into this information as to make sure that it's been limited to a maximum. The third factor for reliability is looking at the variability actually that's built into your model. Variability is inherent to your data. You cannot reduce it like you can try to do it with uncertainty when you're building your model. It's inherent because, for example, it's linked to intra-lab variability, repetition of the measurements, and it's something that you cannot reduce, but you can actually characterize, and you can take into account when you have your prediction. You can take this variability into account, because prediction, and then you just have a bit of an idea of how variable this prediction can be with regards to the data that's put in. Now, this is basically linked to information reliability of your data and input data. A fourth factor, and a factor that's important and which depends a lot on the choice of your model, is the validation state. I already talked to you that you can try different techniques, and when the choice between different techniques is going to happen, we're going to apply what's called validation. We're going to calculate different criteria like specificity, sensitivity of these different models, and this can give you an idea of how good your prediction model actually is, and you can make a choice of the prediction model, and it can help you also to estimate if your prediction is actually a good one. Is it sensitive, specific? Does it have a tendency? If your model has a tendency to kind of over-predict, to tend to predict negative values positive, it's more analytic models, or is it quite equilibrated? So this is an information, a validation information that usually comes descriptions. One also finds it a lot of in articles coming with models that we have to take into account. And then in the last step, especially also when you have all this information, what is very important then also with regards to a regulatory acceptance of these models, and then also use, is grouped under the term reporting, is the idea that you are transparent on all the steps of your process of building your model. You are very transparent about what's your applicability domain, uncertainty, variability, validation. And that's also very much a requirement, I think, for regulatory acceptance. And what's been done is then there have been formats out, reporting formats out, that just for different kind of models help to describe all the factors, the information that one might need to be as transparent as possible about a prediction. And you as a user, if you use a model and there's this format provided, you can actually use this information with your safety assessment and communication actually of your safety assessment internally, but also externally if necessary. So that's basically the last steps. Now here you see a summary of all what you said. I hope, and you're supposed to have kind of got into the indications to in this first part of the presentation. But I suggest actually, because of timing, that we go on to the next part and on to Wendy, if all's clear with regards to read across.
Thank you, Anne. So hi, I'm Wendy. I'm going to talk you through the second part of this presentation on read across. So thank you, Kate. Next slide, please. So we're going to start with the point of what is read across. So basically, read across is an approach that's used to fill a data gap for one substance, which is called the target, for a specific endpoint by using data from another structurally similar or mechanistically similar substance, which is known as the source. So basically, you're taking a data-rich substance and using that data to support your data-poor substance, which is the target. Now, traditionally, read across has been used in both safety risk assessment and in regulatory submissions. Next slide, please, Kate. So there are several different read-across approaches, and it very much depends on what data is available and the properties and how similar your target and source are to each other. So if there's only one substance that's a suitable source, this is known as a one-to-one read-across. And in that case, the data from the source substance is directly used within, for example, the safety risk assessment of the target. So that's one-to-one. Next slide, please. So if you're lucky enough to have multiple source substances, this is known as many-to-one. So the data from all the different source substances is used to support the substance in a sort of consensus manner. So if you have a lot of substances which are structurally similar, but do not follow a particular trend or pattern in their properties, this is called an analog approach. If you've got multiple substances that do have similar properties or which follow a pattern because they're structurally similar, this is known as a group or category. So the example below is an example of a category where you've got a trend in log P due to alkyl chain lengths. So this is just an example to show you. Next slide, please. So normally you have one target structure as your material of interest, and you tend to have one structure in your source, but sometimes it gets a bit more complicated and your target might be a mixture and your source might be a mixture. In that case, you need to do a couple of different things. Now, if you've got a target which is a UVCB, so an unknown variable compositional biological substance, or a natural, for example, that can be incredibly difficult to characterize because you've got multiple structures in a single substance there. Another example is polymers, and in that case you'd use a monomer, shown in the example on the right, to basically perform your read across and identify some source substances. If you've got an inorganic substance, you might be looking at completely different data sets in this case and looking for different types of properties to do your read across. But in all cases, what you've got to show is that your source and target share similar properties and behaviours. Next slide, please. So there's lots of steps in performing a read across, and these can be defined within a framework. So the one on screen is just an example one. Some organisations create their own. There are publicly available frameworks to follow, such as the REACH-RAF, which is a read across assessment framework. In the example that's shown on screen, you can see there's a number of steps involving your target substance, and then a number of steps involving your source, and then an overall outcome at the end. So if we start with the decision context, so basically that's your problem. Why do you think you may need read across? And there's data gap analysis for the target. So you're going to collect all the experimental data for your target that you can find, and then you're going to review it as well. And then there's target profiling. So as well as looking at the existing data that you found during your data searches, you might employ some of the tools that Anne was speaking about in the first session. So you might use some in silico tools to find out more about the potential toxicity of your target substance. We then go on to source. So source identification is obviously, as the name suggests, you're going to find some suitable source substances with data to use in your read across. Once you've identified some, we're going to evaluate them in the next step. So basically, is the data of good quality? Are those source substances structurally and mechanistically similar to your target substance? And in these sort of steps, you might find that you actually reject some of your source substances because they're not suitable. For the ones that are suitable, you take them on to the next step where you're going to look at the data. Is the data of good enough quality to use in the risk assessment of the target? And then finally, when you've reviewed all the data that you've collected throughout all these steps, you'll come up with an overall read across outcome. So just to stress, it's really important to log all the information that you've collected at each point in the read across framework, because that supplies your evidence for supporting the use of the source substances. Next slide, please. So before we go through each of the steps in the framework in a little bit more detail, I'm going to talk about the read across hypothesis. So basically this describes why you think it's possible to use the data from your source substance to support your target. So if your source and target are shown to have the same features, property and behaviour, The hypothesis is that the target would exhibit the same biological response in an assay as the source substance, and this would therefore justify the use of the source data to support the target. Now, your hypothesis might be purely based on structural and mechanistic similarity, or your hypothesis might be based on the fact that both your source and target metabolize to the same thing. So there are different ways of defining your hypothesis, and it does depend on the target and the source substances that you find. So basically, you're going to pick a feature within your within your target substance to define how you think your target substance would behave compared to the source substance. Next slide, please. So first step in the whole of your read across framework is your decision context. So this is basically your problem. So why do you need read across, which is and why are you, what is your purpose? So is it for safety risk assessment, or is it for regulatory submission? And what do you know about your target so far? And then a little bit about your exposure scenario, because this can have an impact later in your read across. Next slide, please. So again, this is our second step in the framework. So we're going to do some data gap analysis for the target. So we need to know as much about the target as possible. So this includes all its data, how it's identified. So there's lots of steps in this. The first one is identifying the target. So basically, you're going to collect all the other names and identifiers that are used for your target. Now, this is important for when you do your next part, which is searching for and collecting data. If you've got some studies that were performed using a different identifier or a different name, you might miss those if you don't fully identify your target first. Once you've collected all your data, we're going to review it and see whether it's good enough to use in the risk assessment for that target. And then we're going to summarize our data gaps. So again, all of these steps you can add to your data matrix. So a data matrix can just be a simple Excel file where you're using different worksheets in the Excel file to collect all these different types of information as you go along. Next slide, please. So then once we've done all that, we're going to summarize our data gap. So our data gap might come from the fact we literally don't have any data, or it might come from the fact that once you've reviewed the experimental data that is available, you might determine that it's not good enough quality to use in the risk assessment. So this in effect gives you another data gap to fill. Now, as read across is endpoint specific, you're going to have to perform a read across each individual data gap endpoint that you're trying to fill. Next slide, please. So on to target profiling. So far along our framework, we've collected an awful lot of information about the target. Now, this depends on how much information is available. If your target is very novel or it's a completely new substance, there might not be much experimental data out there. So this step, this target profiling, tries to supplement your lack of knowledge on your target with some more information. So this includes summarizing the structural features. So obviously structural features can be responsible for toxicity, as we've heard from Anne. So it's important to summarize all the features in your structures. You're going to profile the target. Now the profiling step looks at both your existing data, but also at this point, if you haven't got much existing data, we're going to apply some in silico tools. So we're going to predict the potential toxicity and the potential phys-chem parameters for the target. We're also going to explore toxicokinetics. So we're going to think a little bit about our exposure. So what happens if and when that substance enters the body? And then finally, we're going to look at metabolism in a little bit more detail, as again, Anne hinted that toxicity may come from a metabolite and not the parent substance. So we'd look at both metabolism and the toxicity of the potential metabolites. Next slide, please. So looking at your structural features, now admittedly this step does need a little bit of knowledge of chemistry, but basically because your functional groups within your structure are going to be responsible for a lack of or a presence of toxicity, it's good to know the particular structural components you have in your molecule. So for example, we've got things like alkyl chains, we've got a bit of unsaturation there and different functional groups. So again, I would suggest that you add all these features to your data matrix, because you're going to compare these features with the features that are in your potential source substances. Next slide, please. So a little bit more about the in silico tool. So basically, as I said, Profiler identifies any potential for toxicity either from your existing data or from using in silico tools. So you can use in silico tools to do two main things. You can predict toxicity and you can also predict phys-chem. So in the example I've got there for predicting toxicity, if you've got halogenated alkene, for example, that can be associated with carcinogenicity. So that might be an alert that you get when you run your in silico tools. When you do phys-chem predictions, it will be really useful to use that data to help inform a group or category. For example, the example I gave earlier was log P, or you can look at solubility or various other phys-chem parameters to determine a group or category. It says at the bottom there that if you have got a mixture, you need to repeat this for each component in your mixture. That is assuming that you can identify all the components in your mixture, but it's important to look because some components may have a slightly different toxicity profile than others. And then the output from all of this, again, you'd add to your data matrix. Next slide, please. So this is a very brief list of some of the tools that Anne mentioned. So this is a list of public and commercial in silico tools that you might decide to use to perform either your predictions for toxicity, for human health and the environment, and for also phys-chem predictions. Some of them also indicate mechanism of action or molecular initiating event, which is really useful when you're trying to establish similarity between your target and your source. You need them to show the same mechanism of action or MIE as such. Next slide, please. So a little bit about exploring toxicokinetics. So again, as I mentioned, this is looking at if and when your target substance enters the body. Now, this is really important if you're doing read across for a systemic endpoint, because you need to know what happens to that substance. So the first thing is it's basically looking at ADME, so absorption, distribution, metabolism, and excretion. So by doing that, you're looking at the behavior of your substance within the body. If your substance does enter the body, you might find that metabolism is extremely quick, and your body copes with that chemical really quickly and excretes it really quickly, so that potentially the risk is lower. Now, this sort of data is available in literature and various data sources, but again, if you can't find any experimental data, there are in silico tools available to predict these types of properties. And this is all covered also in another module of the education programme, module 5. Next slide, please. So at the end of everything, we've done everything we can possibly do to the target. We've looked at its features, we've collected its data, we've predicted toxicity alerts where there isn't any data, and all of this summary is in your data matrix, ready for you to compare with the source substances. Next slide, please. So now we're on to identifying our source substances. Now, there is a possibility that if you look in literature or other regulatory dossiers, you might find a similar substance that you can consider for read across. In this case, you basically go on to the evaluation step in that case and see whether that source substance is good enough. If you haven't got any source substances from literature or dossiers, basically you're going to identify them yourself. So this step involves searching for some source substances using the target structure as input. You're then going to review your search results, and you may reject some substances then. If you then come out of that step with some source substances, you're going to identify them fully. This is exactly what we did for the target. So you're looking for alternative identifiers and names, and you're going to look for some data and update the data matrix with that data associated with those source substances. Next slide, please. So when you're looking for source substances and using the target structure, there's two types of searches you can perform. A similarity search, which uses all the whole target structure to find source substances which are structurally similar. So they contain the same features that you've recorded in your molecular structure earlier. The other option is to take a part of your target structure and use that as the input to the search. Now, this may have come from your profiling step. You may have had an alert associated with a piece of a functional group within your target structure that you can then use as the input for your search. Now, in both cases, you can add an extra condition to your search that the search results must have the required data that you need to fill your data gap. So you're putting an extra condition on those search criteria. Next step, please. Next slide, sorry. So quick bit on similarity searches. So as you can see in the example, we've got a target structure, we used a similarity search and we've ended up with a similar structure that's got the same features. To do this, most of the search tools convert your target structure into fingerprints. So it's taking all the structural components in that structure and they're encoding them into strings. And then what it does is it compares those strings with the strings it's got for all the other substances in the database. So all those other substances are converted into strings in the same way that your target structure is. Next slide, please. Now, the other type of search that I mentioned was substructure searches. So if you see from the example below, if your target substance is the middle one, you can see that there's multiple different substructures within that molecule that you could use as input for your search criteria. Now, when you do that, a word of warning with substructure searches, your results will include substances that contain that substructure. But the thing is, they may also contain other features that may be associated with toxicity that your target structure doesn't have. So sometimes it might be good to try and do a combination of a similarity and a substructure search if you can, and then compare the results and define your source substances from those. Next slide, please. So as I said, you might reject some source substances. So there might be missing functional groups, there might be additional functional groups associated with toxicity. The structural feature might be in a ring versus a linear structure. There might be structures that impact properties, for example, the presence of a very long alkyl chain, or you might actually have missing endpoint data, so there's no point considering that source substance at all. So basically anything you reject, it's really useful to log that and log the reason why you might have rejected that substance. Next slide, please. So once we have some source substances from our data searches, basically we're now going to try and find as much information about those source substances as we can. So the first step is to identify them. So you're going to do the same step you did for the target. We're going to look for all the alternative names and we're going to look for all the identifiers that source substance is known by. Again, if it's a mixture, we're going to look for all the component parts of that mixture. And then you can store all of this alongside the data for the target in the data matrix. Next slide, please. So basically, when you're searching for existing data, like I said, it's really important that you know exactly what the source substance is in terms of its identifiers. And it's really useful to get all the existing experimental data, not only to use potentially to support the target, but to see how the substance reacts. And we're also going to log any phys-chem parameters, of course, if we're considering that we might be doing a category or a group read across. So again, all of this goes into the data matrix. Next slide, please. So once we've established our source identity, we've collected some data, we're now going to consider whether that source is suitable for use in the read across. So we're going to repeat some steps here that we did for the target. We're going to profile the source substance, so basically find out its potential for toxicity. We're going to explore some toxicokinetics and we're going to look at its metabolism and the toxicity of its potential metabolites. Once we've done all that, basically we should have a good picture of the source and its suitability for use in the read across. Next slide, please. So once we know everything we can about the source, and we also know everything we can about the target, we're now going to compare them. So we're going to compare structural features, we're going to compare potential toxicity, physical properties, how it behaves internally in the body, if it gets into the body, metabolism, and then we're going to score each of our source substances. So one of the scoring schemes available is the one that's on the right hand side. So you might define that your source substance is suitable for use in read across. You might say it's category 2, it's suitable with interpretation. Now this means it might have a structural feature that the target didn't have, but that structural feature doesn't pose any risk for additional toxicity. So in that case, you might consider, yes, that's fine to use that source substance in the read across. You might say it's suitable with a precondition. So again, this might involve metabolism. So your precondition might be that both your target and your source must share the same biotransformation and must produce the same metabolite in common. So again, that might be, you still might be that suitable for use in your read across. And number 4 is, after all that, when you've done your comparison, the source substance is too dissimilar for you to use in the read across, and then that means it's not suitable. Next slide, please. So traditionally, read across is based on in vivo data, but obviously there's a lot of new approach methods coming into it that are being developed that might help you support your read across. For example, you might decide to do a metabolism study if your hypothesis is based on metabolism and common metabolites forming. So that would confirm that you do get the same metabolite formed and the rate at which it forms. You might decide to do some targeted in vitro studies that help you support the data gap. Now, the examples shown there are 2 assays from Toxis. So Tox Tracker is to do with looking into insights into genotoxicity, and the Tox Profiler looks at cell stress responses, which is again another important indicator for systemic toxicity. The other one you might use is some high throughput assays, for example, transcriptomics, where you're looking at the whole genome, and that might identify toxicity which you might not have identified using the experimental data or the current in silico tools. So all of those can help you inform your read across. Next slide, please. So after all of that, you're going to conclude your read across, and you're going to determine whether the data from the source substance can be used to risk assess your target. So obviously you've used all the information that we've gathered throughout the framework, and then you used your comparison. Is there enough evidence that you've collected to support your initial hypothesis, and is that data of good quality to use? Once you've come to that conclusion, you pop that again into your data matrix to record the outcome that you've concluded. Next slide, please. Now, again, just as you consider uncertainty for in silico tools, you must consider uncertainty for your read across. And this can come in at any point in the read across. It could come in the context of your purpose. Is this good enough to use in a risk assessment or regulation? It could come into your data. Is the data of good enough quality? Is it done to GLP? Is it done to an OECD guideline that's current, or is there some parts of that protocol that are missing? So all of these can affect the uncertainty. There's also like uncertainty in arguing and supporting your hypothesis. Are the mechanisms of action the same? Is there enough weight of evidence to support your hypothesis? And then the bottom one, is your source and target similar enough in terms of structure, properties, potential metabolism? So all of those areas that we've described when we've gone through our framework, you could have an area of uncertainty, and it's really important to document where you think that uncertainty might be. Next slide, please. So documenting the read across is really important. You've done an awful lot of it at this point by doing your data matrix, and that might be all you need to support a safety risk assessment, for example. You might just need to summarise that nicely and pass that to the risk assessor. However, if you're doing your read across for a regulatory submission, you might need to take all that information and put it into a more formal or required format. For example, the REACH read across assessment framework, the RAF. But saying that, if you've done your data matrix, it's really easy to map the components of that into a more rigid template to support the RAF, for example. So documenting your read across should be quite straightforward, hopefully. Next slide, please. So a bit about regulatory acceptance. So read across is by far the most applied alternative approach in REACH submissions. And by doing that, you're filling a data gap by not using further animal testing. Now, there are some conditions and guidelines to using read across and grouping within REACH, and they're listed in Annex 11, Section 1.5 of the REACH regulations. Now, part of that is shown below. Now, if you scan down that, most of the things that are required are the things that we've covered in our read across framework. So there's no reason, once you've followed a framework and once you've documented it fully, there's no reason why your read across should not be accepted as part of your REACH submission or any other regulatory submission. Next slide, please. Now, at the end of this, you might decide that read across isn't enough to support your risk assessment or your regulatory submission. So this is where you might incorporate a weight of evidence. So you might decide to use all your experimental data, some in chemico data, some in silico, tool outputs, read across, and some in vitro data that you've collected from a new approach. Now, all of these can add to a weight of evidence. Now, this is covered in more detail in module 7. So basically, you're just going to determine which piece of information is the most important in your risk assessment for your material of interest. Next slide, please. So this slide is the end of my presentation. I'm really conscious of the time. So I'll hand over to Kate at this point just to wrap up the session.